Hello again, AP Physics students. In today's lesson, we are finally going to begin the actual real course material for AP Physics C, Electricity and Magnetism. Although what we're going to do is we're going to review a little bit of things we looked at back in Physics 30 with electricity and also a little bit of Physics 20 with gravitation. The difference this time around is that we're going to reapproach it by looking at things in 3 dimensions. So in terms of some of the math prep lessons that are required for this particular lesson, that would be the lesson on 3-dimensional vectors, where we're going to worry about writing vectors in the format of an ordered triple, and we're also going to need to make use of the unit vector to help calculate what things like the gravitational field, electric field, gravitational force, or electric force are equal to. Now, before we get into that, I'm just going to quickly talk about something referred to as a vector field diagram. Now, this is a little bit different in comparison to the field diagrams that we drew back in Physics 20 for gravitational fields and Physics 30 for both magnetic and electric fields. Okay, so I have this like really strange looking region where I have like a bunch of little tiny broken arrows in this region being represented by this this y-x plane. Now, if we were to do this in Physics 30, like draw electric field lines would need to be continuous. So what a vector field diagram is it's basically just a regular field diagram that we would draw, except we make the lines a little bit broken. Okay, so instead of it being continuous lines showing the direction, we actually have numerous tiny little vectors that illustrate what the magnitude and the direction would be at various locations. Now, obviously, this would be like tremendously tedious to construct in comparison to like an actual like simplified electric field diagram. So I can't imagine there would ever be a scenario where you'd be required to actually construct a vector field diagram, as much as just making sure you're able to interpret what the vector field diagram looks like. Okay, so let's assume that those vectors we see in the diagram represent the electric field, and this electric field is surrounding 3 source charges. So what I'll do in the picture is I'll just kind of like indicate where my source charges are. So there's one at point R here, there's one at point S, and there's one at point T. Okay, now in addition to a vector field diagram showing you what the electric field would be at various positions like in this 2-dimensional space, the other thing it does is it tells you something about the magnitude of the electric field. Now this is where it gets a little bit weird, because when we sketched electric field diagrams back in Physics 30, if we had a region where we didn't draw very many field lines, that was a region where the field was quite weak. Okay, so the field density was low, then the field strength was weak, or it might have even been equal to 0. Now, in the case of a vector field diagram, it turns out that vectors with really big magnitudes are simply just not shown. So when you see empty spaces on a vector field diagram, that would actually be an indication of an area where the field is really strong. I suppose the logic with this is that if you look at the actual little tiny vectors, as they grow in strength, like the length of the vector gets longer and longer and longer. And I suppose if like the field strength was super high in one region, you'd have like the tails of the vector that are just simply too long to draw in that space. So I suppose maybe that's why we do not draw vectors with large magnitude, just because their tails would just extend too far outward. So just note that difference here in comparison to our previous field diagrams. Empty areas actually indicate regions where the field strength is quite high. Okay, so let's solve a quick example of this. It says the following diagram illustrates the electric field surrounding 3 point charges. So as I mentioned, there's a point charge QR. There's a point charge, There's a point charge at S, and there's a point charge at T here. And what I want to do is I want to identify whether each charge is positive or negative. Now, just as a quick recall, in terms of like figuring out the direction of the electric field, okay, so I'll just write it in up here, okay, so just, whoops, sorry about that. Okay, so just as a quick recall, your electric field points in the direction of a positive test charge. The direction of positive test charge would move. Points in direction of positive test charge. So if you had like a positive source charge, okay, so say this is a big positive source charge. And I wanted to know what the direction of the electric field is surrounding this thing. If you put a positive test charge here, so let's abbreviate test charge of TC, this test charge would want to repel. So what that means is if electric field lines are directed away from a source charge, the source charge must be positive. Or if we have a negative source charge, and you put a positive test charge in that vicinity, a positive test charge would want to, attract towards that source charge. Therefore, if an electric field line is directed towards a source charge, the source charge then must be negative. Okay, so let's go back to our picture and try to figure this out. Okay, so what's going on with charge R? Well, the field lines are directed inward. Okay, so I could say QR is negative since the electric field is directed inward. Okay, so QR is negative. Yeah, because if QR is negative, it means that any positive test charge would be attracted. Same thing with QT. QT also has the electric field lines being directed inward. So we could actually say QT is also negative. And it's negative for the same reason. Maybe I should write that out again. And if you look back at QS, surrounding QS, all those electric field vectors are directed outward. The only way a positive test charge would move away is if that source charge was positive. So we can say QS is positive since the electric field is directed outward. All right. Now, what part B wants me to do is just wants me to compare the magnitude of the three charges, kind of just by looking at the amount of space that is just surrounding that actual that charge. Now, for a vector field diagram, again, we don't show the largest magnitude vectors. So if I look at the picture here, it looks like the space around QR and around QT are about equal, and there's much more space around QS. So that means that QS would actually be the largest magnitude of charge because it has the most empty space around it. Okay, so we could say the magnitude of QS is greater than the magnitude QR, which it looks like QR and QT have about the same magnitude. So QT, and the reason for this is because there's larger empty area around QS, and large magnitude vectors are not shown. Okay, so that just compares like what a regular field diagram would look like in comparison to a vector field diagram. So just make sure we're familiar with how to do both of them. Okay, now we're going to look at our equations for electric and gravitational forces and fields, but we're going to look at them from the perspective of three-dimensional equations. So with the three-dimensional equation, we're going to start to implement the use of the unit vector, which we talked about before. Okay, so with the incorporation of a unit vector, and again, a unit vector is the vector that has that hat on top of it, both the magnitude and direction of a force or field can be calculated using the following equations. So what I'm going to do is I'll show you what just as a quick recall, what the physics 20 or 30 equation would look like, and then we'll kind of beef it up to meet a three-dimensional type equation. And so this is useful for all three-dimensional problems and some two-dimensional problems. Okay, so let's start with the gravitational force, Fg. Now, in physics 20, the physics 20 equation only calculates the magnitude of this force. So the magnitude of the gravitational force would be the gravitational constant, capital G, times m1, m2. Typically, m1 we say is like some larger planetary mass, potentially, and m2 is a smaller mass. And we divide by r squared, where r is the distance from the center of m1 to m2. Now, that only tells you what the magnitude is, but we know the direction of a gravitational field is always directed inward towards a large mass. Now, we're going to beef this equation up by turning it into an equation we can use to calculate both magnitude and direction in one shot. Okay, so here's this equation looks like. We have Fg is equal to negative gm1 m2 over r squared multiplied by the unit vector r. Okay, now there's a few differences here. So first of all, there's this negative sign in front. Okay, this part's the same though. So this part is just we're taking the magnitude gm1 m2 over r squared. So that's identical. And the other different part here is a unit vector. So again, just as like a quick little recall in terms of what this does, is a unit vector is essentially a conversion factor that will take magnitude. Okay, so this box equation here from physics 20 is magnitude. And a unit vector is exclusively going to tell us just what direction the vector points. And I believe this negative here just ensures that the direction of the gravitational force is always going to be towards directed inward, towards like a center of like a large mass. Okay, so then again, what you take the magnitude, multiply by the unit vector, and it's actually going to give us all information about the force of gravity. It's going to tell us both magnitude and it's going to tell us direction. So it's going to give us Fg as a complete vector. Gravitational field, lowercase g, will be calculated by G is equal to capital G, M, divided by R squared. And usually in this equation, like the M value is going to be, I'll say ms for like a source mass. So a source mass is typically like a larger mass. So that could be like a planetary mass. So that just calculates the magnitude of it. But if we, again, just kind of add a bit more to this equation, we would have, if we want to calculate g as a vector, it would be equal to negative gm over r squared multiplied by the unit vector r. So once again, what I can see here is I have the magnitude part of the equation, gm1 over r squared. We're going to multiply by the unit vector, which deals the direction. And this negative is also going to make it so the direction is going to be directed inward. Okay, we'll do some examples in a moment or actually show you how we can do it. Okay, electric force. We refer to it as the electrostatic force in physics, physics 30. We can just call it abbreviated as an electric force now, same thing. Okay, so our physics 30 equation was Coulomb's law. So we have K Q1 Q2 over R squared. And again, that just calculates the magnitude. And the direction of the electric force would just be, well, depends on the actual, it depends on the situation in terms of like which charge you're looking at. Are you looking at Q1 or are you looking at Q2 in terms of what direction it's going to be? Now, this looks quite a bit different. Okay, so what we have here is we have 1 over 4 pi, and we have this little italicized E symbol. That's a letter of the Greek alphabet that is called epsilon. And then we have a subscript attached to it, epsilon 0, or we refer to that as epsilon naught. And then multiply by Q1, Q2 over R squared. Now, if I try to compare this to the physics 30 equation, okay, I only see a little bit of it. Okay, so I see Q1, Q2 R squared, but I seem to be missing K. Well, it turns out this whole part here, the 1 over 4 pi epsilon naught, that is equal to Coulomb's constant. So really the only new thing I have here would just be the multiplication by the unit vector. So that's going to take your magnitude, which Coulomb's law tells you, multiply by the unit vector, and it's going to give me the actual direction of the electrostatic force. Okay, let's clarify that though. 1 over 4 pi epsilon naught is equal to K, which is Coulomb's constant. Now, from physics 30, Coulomb's constant, the value we have in our data sheet is 8.99 times 10 to the 9 newtons times meters squared per coulomb squared. The one that's provided on the information part of the EAP Physics C data table just rounds it to 2 significant digits. So what we would see then is K is 9.0 times 10 to the 9 newtons times meters squared per coulomb squared. Now, in terms of what exactly this value of epsilon naught is, well, if you know 1 over 4 pi epsilon naught is equal to K, you could actually manipulate for epsilon naught and calculate it. But that term epsilon naught has a special name to it, and we'll come back more to this term like throughout the actual unit. It's referred to as the vacuum permittivity, and the vacuum permittivity has a number that looks like 8.85 times 10 to the negative 12 coulombs squared divided by newtons times meters squared. Okay, so it's got like a pretty ugly number to it and some pretty ugly units, but it's also on the data sheet. It's not a number you need to memorize, but again, it's going to be a constant that we're going to use quite a bit once we get into a discussion of something called Gauss's law, which will, again, come in like a few lessons from now. We also have the electric field. So our physics 30 for electric field is the electric field is equal to K multiplied by the absolute value or magnitude of Q divided by R squared. And This right here again is going to be QS, so it's going to be like a source charge that's responsible for producing the electric field. If we convert that into this three-dimensional notation, we'd have the electric field is equal to 1/4 pi epsilon naught Q over R squared multiplied by the unit vector. So again, we pretty much have the physics 30 equation. So 1/4 pi epsilon naught is just K. So KQ over R squared would be the magnitude. Take the magnitude, multiply by this unit vector, and we're going to get the electric field as a vector. Okay, but let's see how this actually works by solving an example. Okay, so yeah, unfortunately I have a three-dimensional grid, which of course is more irritating to deal with in comparison to just a two-dimensional plane. So it says an electron is located at the position R1, which as an ordered triple has coordinates of -2, -3, and -1. Okay, I'm going to try to draw the position of this on here. Okay, so we have my x-axis, we have the y-axis, and we have the z-axis. Generally, the way I'm going to try to identify where this point is I'm just going to first of all figure out where the y coordinates and the x coordinates intersect. Okay, so if you look at the graph here, and I'll just do this in a different color. Let's do purple. Okay, so my x coordinate is -2, and it needs to intersect. It needs to form like a point where it would intersect the y-axis at -3. So if I start at -2, I'm going to try to draw a line that's as best I can. Okay, parallel to the x-axis. That was pretty awful. Okay, so that's an x of -2, and then I want y of -3. So that would intersect. Again, trying to draw this parallel to the x-axis. So that would hit the y-axis at -3. Okay, so my first point here, or the two coordinates would intersect at x of -2 and y of -3. Okay, so I have this intersection point of these dashed lines here. Now, the way to figure out where the actual point is I would just look at the z coordinate then. So what does the z coordinate tell me to do? It tells me to drop by 1. Okay, so this vertical distance is 1. So if I drop by that vertical distance, my point's going to be located about right here. Okay, and actually I'll draw this one in red just to make it stand out a bit more. Okay, so that's where my electron is located. Actually, that's where my source charge is going to be located. Okay, now what I want to do is, again, if we want to, we could just label this here. Here's my source charge. My source charge is an electron. I first of all want to figure out what is the gravitational and electric field generated by this electron at a different point. Okay, and the point I'm interested in is 2, -4, -5. All right, let's try to figure out where that point is. So let's do this in, I'll do green here. Okay, so +2 on the x-axis would be, now we're on this side. Okay, so +2, and it needs to intersect -4. Okay, so as best as I can, I'll try to make this parallel. Parallel to the y-axis. Okay, so that's x of +2, and then I want to intersect that with the y value -4. So we'll start at -4 and we'll go to that point parallel. Just realized my writing of source charge has kind of gotten in the way now. Oh well. Okay, and it intersects right here. Okay, at this point. Now the z coordinate would tell me, okay, after you intersect the x and y points, go up by +5 then. Because a +5 is quite big. Okay, so if I go to this point and I go all the way up by +5, I might end up at a point that's maybe, so let's go to red now and draw it. maybe it ends up somewhere about right, like right here. Okay, we'll say it's right here. We don't need to be perfect with sketching this. We're just trying to visualize what's going on. Okay, I'm going to refer to this as my observation location. The observation location is just going to be the location where I want to figure out the gravitational and electric field. Now, what I want to do is I want to draw a vector that goes from the location of the source charge to my observation location. Okay, and we're going to call that vector vector R. Okay, let's see if I can draw this. Okay, that's brutal, but anyways, it's supposed to be a line that just goes all the way up to this point. Okay, now this would be the vector R. Okay, so vector R is a vector that points from the location of the source charge to the observation location. Now, if you're wondering what is the unit vector, so the unit vector again is just a vector that points in the same direction as my vector R, except it has a magnitude of 1. So if I sketched what that vector would look like on here, it would just be a vector that has a length of 1. So my unit vector might look something like, let's do a different color because you can't see that. Okay, so your unit vector would just be in the same direction as this vector here, except it has a magnitude that's a magnitude of 1. Okay. All right, now we don't really need to worry too much about the diagram here, but I just wanted to kind of like show you like what's going on. Okay, so we have an electron at this position, and we want to figure out what the gravitational electric field is at the observation location. Now, the first thing we need to do is we need to figure out, we need to write this vector, the vector R, in three-dimensional notation. Now, the way we can do that is to write the vector R, like realistically, it's just the displacement vector. So if like you went from the source charge to the observation location, your position would change. So the way in which we're going to figure out what exactly is this vector R is we're going to take our final position, which is the position at the observation location, and we're going to subtract the source charge location. Okay, and we'll do that on the next slide here. All right, so let's go to, that's purple's good. Okay, so I'm going to say R is equal to the position at the observation location minus the position of where the source charge is. And I labeled those vectors as R2 and R1. So I called the observation location position R2, and then I called the source location position R1. Okay, we're going to subtract those two vectors. Okay, R2 has coordinates of 2, -4, 5 units of meters, and I'm going to subtract R1, which has coordinates of -2, -3, -1 meters. Okay, when we subtract order triples, all we have to do is we just subtract the x coordinates, the y coordinates, and the z coordinates separately. So my actual vector R would be, okay, 2 minus -2 would be +4. So this is 4. -4 minus -3 would be -4 plus 3. So that's going to be -1. And then 5 minus -1 would be 5 plus 1, which is going to be 6. Okay, and that's in units of meters. Now, what I immediately want to do is, because when we're going to calculate our gravitational electric fields, we need to use the unit vector. But to calculate the unit vector, we need to know what the magnitude of this three-dimensional vector is. So the magnitude of r here would be equal to, it's going to be the sum of all the different squares. So this would be 4 meters squared plus -1 meters. I mean, you don't really need to put the negative in there, so you're squaring it, plus 6 meters, all squared, and we're going to take the square root of this. If I round that to 2 decimal places, it would be 7.28 meters. Now, if we go back to the first math prep lesson, the way in which we calculate the value of a unit vector is a unit vector, r hat, is equal to the vector r divided by the magnitude of that vector. Okay, so vector r is an ordered triple for -1, 6 meters, and we're going to divide by the magnitude of that vector, which is 7.28 meters. Now, what you're doing here is you're taking a scalar, or you're taking a vector and dividing by a scalar. So all we have to do to determine the unit vector is just take each one of these coordinates and divide by 7.28. So 4 divided by 7.28 would be, so the units are actually going to cancel off here, so 0.549. -1 divided by 7.28 is going to be -0.137. And 6 divided by 7.28 meters is going to be 0.824. And the unit vector is unitless. It has no units to it. Okay, now we're finally ready to start calculating the gravitational and the electric field, which is what part A wants us to do. Okay, so we're going to use our three-dimensional equation. So our equation tells us that the gravitational field is equal to negative, and then we have g m divided by the magnitude r squared multiplied by that unit vector. Okay, and this mass right here is going to be the source mass. Okay, so let's plug numbers in now. So this would be negative. G is the gravitational constant, so 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared, multiply by ms. Well, the source location, at the source location we had an electron, so that's going to be a mass of 9.11 times 10 to the negative 31 kilograms. And then we're going to divide this by r squared. So r is 7.28 meters, all squared. And then we're going to multiply by the unit vector. So the unit vector is 0.549 negative 0.137 and 0.824, and let's close that off. Okay, this looks like a nightmare in terms of what to do here. So here's what I recommend doing, just kind of like step by step. Okay, the first thing I would do is I would just take this and calculate it. Okay, so my calculator, just take -1, because you got to worry about that negative sign right here, and then multiply by the gravitational constant, mass of an electron, divided by r squared. So if you do that, then this would look like G is equal to, that number would be negative 1.15 times 10 to the negative 42 newtons per coulomb. Okay, so that's essentially the magnitude. Aside from the negative sign, that is the magnitude of the gravitational field produced by that electron, which, no surprise, it's super small. I wouldn't expect the gravitational field from an electron to be big. Okay, and then we're going to multiply by the unit vector. So 0.549, negative 0.137, and then 0.824. So this is what the unit vector is going to do. It's going to take my magnitude here, and then by multiplying by the unit vector, the order triple, it's going to turn this into a three-dimensional vector. So if we actually multiply this, and again, what you're doing is you're multiplying a scalar, which is on the outside here, by a vector. So we just multiply every number in the order triple by that value. So this would give me G is negative 6.29 times 10 to the negative 43. And then 1.57 times 10 to the negative 43. And then negative 9.45 multiplied by 10 to the negative 43. And the units would be newtons per kilogram. Okay, so what does this mean? This basically tells you what's the x component, the y component, and the z component of the gravitational field vector. Okay, so I've expressed the gravitational field in as a vector in three-dimensional notation. Okay, let's calculate the electric field. So the electric field, this is part A still. Okay, the electric field, we have E is equal to, we have that 1 over 4 pi epsilon naught business. One over 4 pi epsilon naught Q over R squared, and we multiply by the unit vector. Now, there's no way I'm going to plug, like, I know that 1 over 4 pi epsilon naught is just Coulomb's constant K. So I'm just going to plug in the value of Coulomb's constant K rather than writing 1 over 4 pi times the vacuum permittivity constant, just to save myself some work. Now, we're just going to round it to 2 significant digits. So K is, 9.0 times 10 to the 9 newtons times meters squared per coulomb squared. Did I write kilograms squared in the previous slide? Good. Okay. Okay, so Coulomb's constant times Q. Now, in this equation here, so this is QS, that's the electron. You'll notice there are not absolute value signs around it, so we actually do have to plug in the correct sign of an electron. So that would be 1.60 times 10 to the negative 19 coulombs. And then we're going to divide by R squared. So R is 7.28 meters all squared. And then we're going to multiply by the unit vector. So again, that unit vector is 0.549 negative 0.137 and then 0.824. And then once again, just to not overwhelm myself with calculations, what I'll do is I'll first of all just calculate this part, like calculate every part that's outside of the unit vector, outside of the order triple. So then this would look like the electric field strength would be equal to, this is kind of nice too, because it also shows you what the magnitude of the field is. So this would be negative, because you have the negative charge of an electron, so negative 2.72 times 10 to the negative 11 newtons per coulomb. Okay, so this number is the magnitude of the electric field. I mean, magnitude of the electric field, not including that negative sign. and then we're going to multiply by the unit vector. So 0.549, negative 0.137, and then 0.824. And then this is going to give me the electric field strength would be equal to, and you can already see it's going to be a lot bigger than the gravitational field strength, and the force of gravity is pretty small compared to like an electrostatic force. So this is going to give me negative 1.49 times 10 to the negative 11, comma, so again, we're multiplying every number in the unit vector by the number on the outside, 3.72 times 10 to the negative 12, and then negative 2.24 times 10 to the negative 11, and the units are newtons per coulomb. Okay, so that's my answer for part A. Now, part B says, let's say we put a second electron at R2. I want to calculate the gravitational and electric force acting on that electron at that point. Okay, so just remember, like a field is a region of influence, of potential influence. I mean, yes, we have a gravitational electric field at the observation location, but it doesn't do anything until you actually put something there. Okay, so now we're going to put an electron at this point, and we're going to figure out what is the gravitational electric force acting on this thing. Okay, the easiest way to do this is, rather than using the equation for Coulomb's law, or for the equation for Coulomb's law, or for universal gravitation, let's just calculate Fg like we would the weight of an object. Okay, so what we know is that Fg is equal to mass times g. Okay, so this would be equal to, what's the mass? Well, it's the mass of the electron at that observation location. So again, this is, just be aware that this is the object at the observation location. Okay, so that would be, well, it's another electron, so 9.11 times 10 to the negative 31 kilograms, multiply by the gravitational field, which we calculated on this slide here. So we're going to multiply by all these numbers. So multiply by, so what do we have again? We have negative 6.29 times 10 to the negative 43. We have 1.57 times 10 to the power of negative 43. And we have negative 9.45 times 10 to the power of negative 43. And the units are newtons per kilogram. So you can see here that the units of kilograms are just going to cancel off when we do this. kg goes away. All right, so all I'm going to do is multiply this number by every number in the order triple, and that'll give us the gravitational force. So our gravitational force, Fg, would then be equal to negative 5.73 times 10 to the negative 73, 1.43 times 10 to the negative 73. Again, this force is so ridiculously small. And then negative 8.61 times 10 to the negative 73. And the units are going to be newtons. Okay, so that's the gravitational force that acts on that electron at the observation location. And again, the vector notation just tells you what the component of every, the x, y, and z component of that force would be. Now, we can do a similar thing for the electric force. So we can calculate the electric forces just by drawing a perfect analogy with the gravitation equation. So instead of Fg, we're going to write down Fe. So we'd have Fe is equal to, instead of mass, we're talking about charge. So we'd have Q. And then instead of the gravitational field, we have the electric field, which would be E. Okay, so once again, this Q value is the charge at the observation location. So let's multiply things out here. So at the observation location, we have another electron. So it's going to be, and again, this is not absolute value of charge in this equation. This is the actual charge, 1.60 times 10 to the negative 19 coulombs. I know in physics 30, we typically in this equation wrote everything down in absolute value. Well, that's because we weren't doing vector math then. We were calculating the magnitude and the direction of the forces and fields separately. Okay, so we're going to take this and multiply by the, oops, I don't know why I wrote that as an order triple. Let's put it in just regular round brackets. Okay, we're going to multiply by the electric field. So the electric field is x component, negative 1.49, 10 to the negative 11. Y component, 3.72, times 10 to the negative 12. And then the Z component is negative 2.24 times 10 to the negative 11. And the units are, this time around, newtons per coulomb. Okay, let's multiply these things by this number on the outside, and we're going to get the electric force acting on that electron at that location would be equal to 2.38 times 10 to the negative 30. It's still really small. I mean, that's no surprise. A single electron does not have much of a region of influence, whether it's through its electric field or its gravitational field. Negative 5.95 times 10 to the negative 31. And then we have 3.58 times 10 to the negative 30. And the units are newtons. Okay, so that shows how we can use some three-dimensional equations and incorporate the unit vector to actually tell us both to tell us what the electric force, gravitational force, electric field, gravitational field is as a vector, as opposed to just identifying magnitude and direction separately. Okay, so that's it for this lesson. And then in the next one, I'm going to introduce you to what an electric dipole is, and then we're going to do some calculations with electric dipoles, and I'll talk to you then.